Okay, you can start your session. Enjoy.
Okay, sweetheart, you okay? You unmute yourself.
Oh, I'm sorry.
Okay, yeah.
Okay, so welcome to the Best Paper Award session. The Asiacrypt 2020 Program Committee selected 3 papers as the Best Paper Award. In this session, each of the best papers will be given a 30-minute slot, and the author of each paper will give us a 30-minute live talk, including Q&A. The first paper is Finding Collisions in the Quantum World, Quantum Black Box Separation of Collision Resistance and One-Wayness by Akinori Hosoyamada and Takashi Yamakawa. Akinori, are you ready for the presentation?
Yeah, I'm ready.
Yeah.
Can you hear me? Okay.
Yes.
And then I'm going to share my slide. Okay, so can you see my slide?
Yeah, not yet.
Not it. Okay, I'm sorry. So I'm trying again, and okay. Can you see the slide?
Yes. So could you start?
Okay. So then I will start. Thank you for the introduction. I'm Akinori Hosoyamada from NTT Secure Platform Laboratories and Nagoya University. Today, I want to talk about the impossibility of quantum black box reductions from collision-resistant hash functions and one-way permutation or trapdoor permutation. And this is a joint work with my colleague, Takashi Yamakawa. First, let me begin with a very basic introduction. As you know, in cryptology, we study many cryptographic primitives. For example,
excuse me, Akinori. It seems that only half of the slide can be seen from here. So could you listen to the stats?
Oh,
could you try again? Yeah. It seems good.
Is it working?
Yes, yeah, great. Thank you. Thank you for interrupting.
Let me continue again. And so in cryptology, we study many cryptographic primitives. For example, we study one-way permutation, which is a permutation easy to compute but hard to invert. And we also study collision-resistant hash function, which is a length decreasing function, hard to find a collision. And trapdoor permutation, which is a one-way permutation, efficiently invertible with a trapdoor, and public key encryption, digital signatures, and so on. And in the theory of cryptography, one of the very most important and fundamental problem is to study the reducibility between cryptographic primitives. And for example, we say a primitive P can be reduced to another primitive Q if there is a construction that constructs an implementation of P from the implementation of Q, and there exists a proof such that if there exists an adversary that breaks this construction, then we can make an adversary that breaks the implementation of Q. If we have such construction and proof, we say that a primitive P can be reduced to the primitive Q. And so now this picture shows the relationship of reducibility between cryptographic primitives. For example, we can make one-way functions from collision-resistant hash functions, or equivalently, we can reduce one-way functions to collision-resistant hash functions. And similarly, for example, we can make public key encryptions from trapdoor permutations, and so However, after seeing this picture, we notice that it seems very hard to make collision-resistant hash functions only from one-way functions or one-way permutations, or even from trapdoor permutations. And so now we have a very natural question. Can we show impossibility of reduction from a primitive P to another primitive Q? This is a very natural question. And actually, such a question of impossibility of reductions is also one of the most important and fundamental problems to study in the theory of cryptography. And actually, unconditional proof of impossibility seems very difficult. So usually, we restrict class of reductions. And in particular, often we focus on the class of black box reductions. And we try to show the impossibility of black box reductions. And so next, let me explain about the black box reductions. We say that a reduction is a black box reduction if both of the construction and the proof are done in black box manner. That is, the construction of P, access to the implementation of Q only in black box manner, and in the security proof, the adversary against Q, access to the adversary against P only in black box manner. Actually, this is the explanation of the fully black box reductions. But in this talk, when I say black box reduction, then it means fully black box reductions. And when we restrict ourselves onto this black box reduction, then we can show the impossibility of reductions like this. In particular, we can show the impossibility of reductions from collision-resistant hash to one-way permutation or even trapdoor permutation. As I showed in the previous slide, in the classical setting, there is no black box reduction from collision-resistant hash to one-way permutation. This is the very fundamental and important result in the classical setting. And next here, I'd like to move from the classical setting to the quantum setting. As you know, quantum computation is more powerful than classical computation. For example, Shor's algorithm breaks the Asiacrypt system, and the reduction from LWE to the worst case lattice problem by relief is given as a quantum reduction. And so after seeing such quantum power, we had this question. Does the impossibility results in the classical setting still hold if we allow quantum black box reductions? This question is the starting point of our research, and we showed these results. In our paper, first, we formalized quantum black box reductions and showed these theorems. There is no quantum free black box reductions from collision-resistant hash to one-way permutations, and there is no quantum free black box reduction from collision-resistant hash to trapdoor permutations. These are our main results. Next, I'd like to explain about how we can prove the impossibility of black box reductions from collision-resistant hash to one-way permutation in the classical setting. So actually, in the classical setting, to show the impossibility of black box reductions, we can use a useful technique called two-oracle technique. So what is two-oracle technique? Suppose that there exist two oracles, phi and psi, such that there exists a secure implementation of Q, but there does not exist secure implementation of P relative to phi and psi. Then the two oracle guarantees that there exist no black box reductions from P to Q. And this is the two oracle technique. And now we wanna show the impossibility of reductions from collision-resistant hash to one-way permutation. So now we want to show there exist two oracles, phi and psi, such that there exists one-way permutation, but there does not exist collision-resistant hash relative to these oracles. if we can show the existence of such oracle, then the two oracle technique guarantees that there is no black box reactions from collision resistant hash to one-way permutation. Next, let me about a little bit more details about this phi and psi. For collision resistant hash and one-way permutation, we set phi to be just a random permutation f, and we set psi to be an oracle called call finder. This oracle takes a description of a function f as input, and here the function f may query to random permutation f, and this oracle outputs a collision of f. And under the setting that these oracles are available, collision resistant hash does not exist, because when the adversary queries the description of the description of some functions, hash functions, to this call finder oracle, then this call finder oracle will return the collision of hash function to the adversary. And so, to use the two oracle technique, what is left to show is that inverting random permutation f is difficult, even if the additional oracle call finder f is available. If we can show this claim, then it means that there is a one-way permutation, because this random permutation becomes a one-way permutation. And to show this claim, we can use a useful technique called compression technique. So what is the compression technique? In this technique, we try to construct a compressing scheme which consists of encoder E and decoder D. And here, the encoder E takes the truth table of random permutation f as input, and output a compressed version of the truth table. And the decoder D tries to recover the original truth table of permutation from the compressed version of a truth table. And in this technique, we show that if the adversary A, if there exists an adversary A that inverts random permutation with a small number of queries, then we can construct a compressing scheme such that after the compression, the truth table becomes very small compared to the original size of the original truth table. And if we can show the existence of such compressing scheme, this yields a lower bound for Q. Q is the number of queries made by the adversary. So this is the compression technique, overview of compression technique. And next, let me explain about a little bit more detail about the decoder, encoder E and decoder D. So first, the encoder E takes the truth table of a permutation F. And the encoder E just partially posits the values of the truth table. And the decoder D tries to recover the truth table by using the adversary A. And next, let me explain about details about the decoder. And so now there is a decoder D, and D wants to recover the original truth table from the partial truth table. And so the decoder D tries to recover F inverse Y, the value F inverse Y for each Y. And first, the decoder D simulates oracles F and call finder, and runs the adversary A on the input Y. And if the adversary A returns X, then the decoder D guesses that the value F inverse Y is equal to X. Roughly speaking, this is how the decoder works. However, actually, there is a non-trivial issue. The issue is the decoder D has to simulate oracles only with a partial truth table of F. And in the classical setting, this issue can be solved by cleverly choosing the set of forgotten points. So roughly speaking, this is how the decoder works. And this is how, in the classical setting, we can show the impossibility of reductions from collision-resistant hash to one-way permutations. And so next, let me explain about what will happen when we try to generalize the classical proof of impossibility into the quantum case. And I will also explain about an important previous work. So again, even in the quantum setting, what we want to show is the hardness of inverting random permutation F for the quantum adversary A. However, now the issue is all the queries are done in quantum superpositions. So the adversary A queries the inputs to F in quantum superpositions, and the adversary A queries the description of functions to the call-finder oracle in quantum superpositions. And now please note that the description of F function or implementation of functions are also quantum circuits. So the adversary A queries to the call-finder oracle the quantum superpositions of quantum circuits. So the proof for the quantum setting becomes very hard. And when we try to generalize the quantum impossibility proof to the quantum setting, we have some issues. First, the choices of forgotten points in the encoder E in the classical setting crucially relies on that A's oracle queries are classical. And second, in the quantum setting, the permutation F cannot be perfectly simulated only with its partial truth table, because the adversary A may query all the inputs in uniform quantum superpositions. So it seems difficult to directly extend the classical proof into the quantum setting. So here, let me simplify the problem like this. That is, please consider the situation that the adversary A has access to only a single oracle, the oracle of random permutation. And actually, the hardness of inverting random permutation for quantum adversary is already proven by Naive et al. In a previous work. And they showed that random permutation is hard to invert for one adversary that can make quantum queries to the permutation oracle. And here, adversary means quantum adversary. And actually, they proved a stronger claim that this claim still holds, even if the adversary obtains some classical advice. However, in our study, we are not so much interested in such classical advice. So in this talk, I just ignore such classical advice. And next, let me explain about how Naive et al. Proved this claim, the hardness of inverting random permutation. And actually, they also used the compression technique. So next, I will explain about how their encoder works. So first, their encoder takes a random subset R, and the size of random subset R is about 2 to the power n over polynomial of 2. And their encoder takes a subset GF inside R. And this is the set of X inside R such that the adversary A successfully inverts Fx. And the adversary A's quantum query magnitude on R is very small. And let GF tilde be the image of GF. Then their decoder, their encoder forgets values of permutations in this hole. And let F tilde be the partially defined permutation, which is defined outside GF. And this partially defined permutation F tilde matches the original permutation F outside GF. And finally, their encoder outputs the pair of F tilde and the description of this subset GF tilde. This is how their encoder works. And next, let me explain about their decoder. So again, the decoder D tries to recover the value F inverse Y for each Y. And the decoder D runs the adversary A on Y relative to a function HY. And here, the function HY is defined like this. HYX is always equal to F tilde of X if X is outside R. And HYX is equal to Y if X is inside R. Then this function HY can be simulated by using only with the partial truth table F tilde. And by definition of the good subset GF, this function and sorry, this is F. This function HY and the original permutation F are indistinguishable. And since A cannot distinguish HY from F, the adversary A outputs F inverse Y. And the decoder D can recover the value F inverse Y. This is how their decoder works. And so by using such compression technique, in addition to the construction of the encoder and decoder, they showed that if the number of queries Q becomes small, then the good subset, the size of good subset GF becomes large. And if the good subset becomes large, then the size of the truth table after compression becomes small. And actually, we have some information theoretic lower bound for the size of truth table after compression. And so finally, we can obtain a lower bound for Q. And they showed that Q is lower bounded by 2 to the power n over 2. And this lower bound matches the upper bound given by Grover's algorithm. So this is how Naive et al. Showed the hardness of inverting random permutations. And next, I'd like to explain about our proof. So recall that what we want to prove is the hardness of inverting random permutation F in the setting that the two oracles F and the additional oracle call finder is available. And the adversary A queries the description or quantum circuits of function, some functions to call finder oracle. And again, we use the compression technique. And so first, I will explain about our encoder. So first, our encoder takes a random subset R as well as the previous work. And the size of R is again 2 to the power n over polynomial of Q. And we again take a good subset. And this subset is completely the same as the subset, good subset in the previous work. And next, we also take an additional subset, random subset R prime. And here, again, the size of R prime is about 2 to the power n over polynomial of Q. And actually, this random subset R prime, additional subset, will later be used to deal with the additional oracle call finder. And next, we also take an additional subset GF2 inside R prime. And this is the set of X inside R prime such that the adversary A inverse Fx and the adversary's quantum query magnitude on non-good circuits are very small. And here I'm talking about the query to the call finder oracle. And here the good circuit is defined like this. A circuit C is said to be good if the value call finder of C can be simulated only with the partial truth table of F outside R prime. And actually, how to formally define such good circuit, or how to come up with the definition, such definition of good circuit is the technical core of our paper. But since I don't have enough time today, so please check our paper for details. And next, I define a good subset GF to be the intersection of GF1 and GF2. And next, finally, as well as the previous work's encoder, our encoder forgets the values of random permutations in this hole. And again, let F tilde be the partially defined permutation, which is defined outside GF. And let GF tilde be the image of GF. And our encoder finally outputs the pair of F tilde partially defined permutation and the description of GF tilde. This is how our encoder works. And next, I will explain about how our decoder works. So again, the decoder D wants to recover the value F inverse Y. And the decoder D runs the adversary A on the input Y. And D simulates F by using HY And this HY is completely the same as the HY in the previous work. And now the issue is the decoder D also has to simulate the additional Oracle call finder. And the adversary queries some quantum circuits that implement functions to call finder Oracle. But here, now, by the definition of good subset, we can say that the quantum query magnitude on non-good circuits is very small. And this means that intuitively, most of the queries made by the adversary are good. Most of the queries to call finder are good. And by definition of good circuits, the decoder D can simulate the value of call finder only with the partial truth table F tilde. So the decoder D can intuitively the decoder D can correctly simulate the call finder Oracle. And so the adversary A outputs the correct output, and D can recover F inverse Y. And so, so far, I have explained about how we construct our encoder and decoder for the compression technique. And finally, we obtained a lower bound for Q, and we showed that Q is greater than 2 to the power n over Q is greater than 2 to the power n over 8. And this means that there exists one-way permutation relative to F and call finder. And thanks to the two-oracle technique, we can say that there exists no quantum black box reduction from collision resistant hash to one-way permutation. And actually, today I don't have enough time to explain about the details for trapdoor permutation. But the proof for trapdoor permutation is not so much different from the proof for one-way permutation. And so finally, let me summarize today's my talk. In our paper, we formalized quantum black box reactions, and we showed impossibility result of quantum black box reactions from collision resistant hash to one-way permutation or even trapdoor permutation. And here, finally, let me introduce some open problem. I think that it would be interesting to consider about other black box impossibility results in the quantum classical setting. For example, in the classical setting, there is the impossibility result of reductions from collision resistant hash to trapdoor permutation plus indistinguishability of facilitation, or from key agreement protocol to one-way permutation. So I think it would be interesting to study about these results in the quantum setting. That's all. Thank you for your attention. And thank you so much for, I'm very honored to be awarded as a best paper award. Thank you so much. Thank you for your attention.
Thank you very much for your talk. It seems that I cannot see the any questions at Zulip chat, please. Does anybody have questions or comments to this question, to this talk? No. So I have a short, quick question. What is the biggest breakthrough in this work?
Actually, the hardest part was the hardest part is how to define a good circuit here, because in the classical setting, all the queries are classical, and for example, in the classical setting, when the query is not good for the decoder, then we can say that this query is bad, and we stop to consider about this query or something like that. But in the quantum setting, we cannot say something like that, because if we measure the query made by the quantum adversary, then it will disturb the whole quantum state. So we cannot observe the quantum queries. And I cannot say details here because it is somewhat complex. But yeah, the difficult the most difficult part was how to define a good circuit here.
Okay, thank you. And we have a question for you from Yevgeny. Could you say?
Okay. Me?
Can you
Yeah.
see the quick?
So this is the question from Yevgeny. What is the difficulty of extending the original IR 89 result about OWF and the key agreement to quantum setting? It is on the chat.
Okay.
Can you see?
So, yeah.
Or
Yes, I can see. Actually, yeah, so it's difficult. The first difficulty is how to formalize the problem, because when we allow, for example, when we allow quantum communications, then we can just use the quantum cryptography or quantum, so-called quantum cryptography to share the secret keys. So to make the problem meaningful, we have to restrict ourselves on the key agreement protocol with classical communications. But actually, it is somewhat hard to treat such problems. And yeah, actually, we tried to solve the problem, but we completely don't know how to prove the theorem, how to prove the claim actually.
Okay, thank you very much. So, so it's time now. So, thank you very much, and let's go to the next best paper.
Thank you.
Thank you. And next talk is new results on Gimli. Full permutation distinguishes and improved collisions by Antonio Flores Gutierrez, Gato Roland, Maria Naya Plasencia, Leo Pelan, Andre Slottenloher, and Ferdinand Schubleilas. And are you ready for the presentation?
Yes, if you can hear and see me. I'm going to try to share my screen.
Yes, yes.
Hello. All right. So can you see everything? So
Yes.
okay, great.
Yes,
so thank you for the introduction. So this is the joint work with these people from INRIA, and I'm going to present some cryptanalysis results on the permutation and NIST candidate Gimli. All right. So the context of this work is the NIST lightweight crypto project, which is now in the second round, and there are 32 candidates which are still here, and 19 of them are based on permutations using sponge and duplex-like modes, for example. Gimli is one of these candidates. It's specifically intended for cross-platform usage. It's based on the permutation Gimli, which was published at CHEST 2017, and which was said to be designed to achieve high security with high performance. And Gimli uses a duplex mode for authenticating encryption and sponge for hashing. So our results include several attacks on Gimli, the permutation, and the hashing mode. So we designed a distinguisher on the full permutation, which has a practical version on 23 rounds on 24. And also improved collision and symmetry start collision attacks on reduced versions of Gimli hash. We also study statistical properties of the permutations. So we perform a first study of linear trails in Gimli, and we designed differential linear distinguishers up to 17 rounds. So in this talk, I'm going to, let's say, first introduce the design, and then I'm going to detail how the distinguisher and the permutation works, and then say a few words about the other results, so collisions and statistical properties. Okay, so gimli, as I said, is a permutation, so it doesn't have any key. It's a keyless primitive that operates on a 384 bit state. So this state is going to be divided in 4 columns that we name A, B, C, and D of 96 bits, and each column has 3 words of 32 bits that we name X, Y, and Z. And the permutation has 24 rounds, which are numbered from 24 to 1, decreasing order. And each round applies what is called a substitution permutation box on each column separately. And then every 2 rounds, there is a linear layer, which consists in swapping some words X between some pairs of columns. And every 4 rounds, there is constant addition, which serves to avoid symmetries. And the constant is added in a single word in column A. So graphically, here is what it looks like. You have 20, so I'm representing a few rounds. You start by round 24, and you have this SP layer, and then a swap. So at this point, this is a small swap. So we swap between A and B and C and D. And then there is constant addition. And we continue. At round 23, there is only an SP layer. Round 22, there is a SP layer. And then there is a big swap between A and C and B and D. And we go on. So since gimli was first published as standalone primitives, there have been some works against the permutation itself. And then there have been more recent works against the NIST candidate. So against the permutation, you can cite Hamburg that crafted the distinguisher on 22.5 round gimli. Was based on meet-in-the-middle approach and using some internal symmetries. On the cipher and hash function, Liu, Isobe, and Meyer found 6-round collisions, 5-round preimages, and 9-round state recoveries. So I must say that our results do not invalidate any security claims that were made in this proposal. And we only target register versions of gimli cipher and gimli hash. So however, we could increase significantly the number of rounds reached in collision attacks. And also, it was a bit surprising to us to find an efficient distinguisher. As I said, it's practical on 23 rounds. So since I'm talking about it, let's dive into the details of this distinguisher. First of all, what is a distinguisher from a permutation? Because you see, a permutation is a keyless primitive. So when you have, for example, a block cipher, you can say we select the key at random, and then we want to distinguish the cipher with this randomly selected key from a random permutation. With a permutation itself, with this permutation itself, you can't do that because obviously it's not random. It has a specific design. So we're going to define. We're going to do things differently. We're going to define some generic property, P, that relates inputs and outputs to this permutation. And we show that if we had only a random permutation with black box access, it would take some time to obtain a valid tuple for this property. And we show that this permutation that we're studying has actually some structure that can be exploited to find a faster algorithm to satisfy this property. A very well-known example of that is limited birthday distinguishers, where you take a vector space for the inputs and a vector space for the outputs, and you're looking for a pair of input outputs with a sum in the input vector space and a sum of images in the output vector space. And in these distinguishers, we use various techniques that are borrowed either from block cipher cryptanalysis or hash function cryptanalysis. In our case, so in gimli, the property that we're going to use is column symmetry. So we're going to say that a gimli state is true identical if you have column B and D equal or A and C equal up to a linear layer. If you have a random permutation, with the same bit size, finding a two identical state that maps to a two identical state takes some time. It takes time to do the 96. The idea is that this is a very nice property, actually. If you have a two identical states, let's say B equal D, after 4 rounds, it's still two identical, because the words that you're actually swapping in the swap layer are the same, so the columns remain equal. And then if you have a single word condition, let's say these two branches here must be equal, then you're going to traverse 4 rounds more. And then we start to see that this property has, this property is going to traverse many rounds with a very low cost. Okay, in order to perform this, we're going to start from the middle, and we're going to ensure that the state at round 16 is symmetric. So here you can remark that actually we're starting from 123, so this will be a reduced round version. We have removed one. Okay, so if we ensure a symmetric state here, going backwards, we observe that so these two columns are going to remain equal for 4 rounds, but then these two branches are equal, so columns A and C are going to remain equal for 8 rounds. So we have 8 rounds for free. And you simply have to choose this state so that it's symmetrical. We still have many degrees of freedom, and let's start to exploit some of them. We're at round 15 now, and we want to select the values of this state. So we're going to select arbitrary values for 2 words, but we simply can't make anything of it. And we're going to use the 32-bit degree of freedom on the 2 other red branches here in order to have a collision in the output. A collision here and here at round 11. This is going to be nice, because if you have a collision here, then we simply have to ensure that columns B and D are equal, and this is going to remain, they're going to remain equal for 8 rounds. So we're already traversing round 23 to round 8. But we still have many degrees of freedom unused, so we're going to use some of them. Now we're zooming out, and we're seeing the state at round 11. At the state of round 11, we have fixed many values now. We have fixed the 2 black and red arrows, but all the rest is still free. So we're going to choose a value for the orange word here, which is actually, well, this is actually a single, there is actually a single word here because they are supposed to be equal up to a constant addition. And again, we choose it so that 4 rounds later, we have a collision. So equal branches. And if you have a collision, then we traverse 4 more rounds. And now the distinguisher is going to from round 23 to round 4. And we still have unused degrees of freedom. The unused degrees of freedom that we have are the green branches here. And now we're going to choose them, finally. And this is going to complete the state in the middle. And we're going to choose them so that 8 rounds later, there is a collision. And if we have that, with this single word condition, this is going to remain 2 identical right until the output, until round 1. So by constructing the state part by part, we were able to create a middle state so that the corresponding input is 2 identical. And the output is also 2 identical. And so we constructed an input that maps to a 2 identical state with so something that was that validates our property. And this is going to, so for this 23rd round version, it costs us time 2 to the 32. And if we want to include the first round now, there is another swap that must be traversed. So there is a 32-bit condition that we need to meet again. And we're going to need a time to the 64, but it's still much below the generic time to the 96. So with similar ideas, or well, ideas that look similar, we're going to attack resistant versions of gimli hash and try to find the collisions. So what is gimli hash? It's a sponge. It's using gimli in the sponge mode. So pi here is a permutation gimli. The state is divided in two parts, the rate of 128 bits and the capacity. And message blocks are XORed on the rate. And then in the end, the hash is extracted into different blocks. So the rate part is actually the X word in each column. So AX, BX, CX, DX. And the capacity is the rest. So basically, if we want to, well, our strategy to obtain a collision is to find a pair of, find different values to inject in these X words so that the output capacities collide. And if we have a collision in the output capacities, then we can inject the right messages and obtain a full colliding state. And then we have a collision in the hash. So this is our goal, right? We're going to make things a bit easier for us by putting the difference only in a single column. So we're still controlling all the X inputs, but now there is only a difference here in A. And the rest, well, we control the values, but there are no difference. It's just a single difference, BX, CX, DX. If we're able to make the difference occur only in a single column, it's a bit easier to collide on the capacity because there are now only 64 bits of collision to obtain in the end. So we're controlling this. We're controlling the input. If we want the difference to remain in the first column, we need some internal collisions to occur. We need the values here that come from the swap to collide for these two different inputs. We need the values here to collide also, so we need all the red branches to collide, basically. And we need, of course, the output to collide as well. But we do not only control the input AX and AX prime, we also kind of control the blue branches here that come from the rest of the state. And if you count the number of degrees, the number of constraints and the number of degrees of freedom that we have, actually, we can expect that there is, on average, a single solution for these two inputs here and the blue inputs that will meet all the conditions. And we can find this in about in a time about 2 to the 32. So having a single difference in the column A, we can ensure that there is that the difference remains in A and that there is a collision in output. In order to find that, we need to solve double SP box equations. So equations that relate the inputs and outputs to this block, which is a double SP box. But actually, it's actually very easy to do. We did that with a SAT solver. And it doesn't well. It's not trivial, but it's cheap. In the sense that solving 2 to the 32 double SP box equations is practical. Next, with this 8-round version of gimli, since we have BX, CX, and DX that we control, we're not going to take values for them that match the blue branches that we want. And this is also done by solving a lot of double SP box equations. But globally, this 8-round collision attack is going to work in time 2 to the 32. So it was practical. If you want to increase the number of rounds, well, each time we add 2 rounds, we have another word condition to meet. So the time is going to increase by a factor 2 to the 32, which is why we arrive at 12 rounds with a time 2 to the 96, basically. And the quantum setting is going to be improved a bit. And also, in the semi-free start setting, it's going to be a bit better, because in the semi-free start setting, we don't only control BX, CX, and DX. We can actually start from the middle And we can we can completely select the values for the columns B, C, and D. So we can start from the middle, and we can satisfy more conditions on these blue arrows. All right. So there are many different collision attacks that we can make. I'm going to say a few words about statistical properties. So in the permutation, we first search for linear trace, which was apparently the first study of linear trace in permutation. I wanted first to have a look at iterative trace, in particular iterative trace that are going to have no weight on the input and output X words, because X goes through the swaps. And if there is no X, then we completely traverse the swap layer. The optimal such tray for a double SP box has a correlation to the -26. Here it is. For 4 SP boxes, we can do a bit better. And we don't know if the trade obtained is optimal. It has correlation to the -47. There are many more examples of linear trace that are given in our paper. And the best trade that we found, which is basically obtained by concatenating smaller trays, it reaches 16 rounds with the correlation to the -150. In order to attack more rounds of gimli with statistical properties, so linear differential, we used a differential linear attack, which consists in using a high probability differential trade and high probability linear trade together. So we split the permutation in 3 parts. In the 5, so we attack here a 17 version of it. In the 5 first round, we use a differential trade, which has a rather high probability. This was given already by the designers. In the middle, we suppose that the initial differential trade is met, and we evaluate experimentally the bias. If you take a pair with this difference, we evaluate experimentally the bias in all output bits. And we find that there is one of them, Z0 in some column, that gives a rather high correlation. This is an experimental part. And this part traverses 9 rounds. And finally, we complete this by studying linear trace that start from this bit. And we have a look at the correlation for the final rounds. And in this final step, we can traverse 3 rounds with the correlation to the -16. And now this gives a distinguisher that simply encrypts per, computes the permutation on input pairs and has a look at the correlation in the output. And this complexity depends on the probability to traverse the differential and then the correlation for the linear part. And find that this gives time to the 154.8 for a distinguisher. And it also yields an attack if you use gimli within an evenmancer cipher with 17 rounds. So evenmancer cipher would be XORing a key. Okay, so conclude briefly. In this work, so we had this symmetry-based distinguisher on the full gimli permutation, and we also obtained the current best collision and semi-free start collision attacks. And we also performed a study of linear trace and differential linear distinguishers. Now, all of these results work by exploiting the simplicity of the linear layer. In the distinguisher, for example, we don't use the specifics of the SP box. We don't use the specifics of the round constants. And we use simply the overall structure of the permutation. So it may be possible to circumvent these attacks by, for example, using another linear transformation than the swaps, which was a possibility that the designers of gimli mentioned. It would be also possible, for example, to swap every round instead of every 2 rounds. And I believe that all of these possibilities are worth investigating. So all of the details are in our reprint report, which is the following. And that's all for me. I thank you for attention.
Thank you very much. Anybody have any questions or comments to this talk? Nothing. I can see any comments in the chat space. So okay, so you did a very great attack on the cryptographic primitives, lightweight primitives. What is the message or some lessons from your work for designing a new primitives?
I guess you could say that well the linear layer is very important. So in all these attacks, as I said, they mainly work because the linear layer in Gimli is very simple. It's only swapping, and so you have this possibility, the possibility to exploit nicely this structure. So none of this would work if there was a very complex linear layer. So I guess well, I think if you read the specification of Gimli, somewhere the designers said they did not find a compelling reason to use another linear layer instead of the swaps. And well, now after this work, I think we believe that there is a compelling reason to do so, because the swaps simply they simply put too much structure that can be exploited.
Okay, that's it. Thank you very much. Any other questions or comments? I think so. Let's thank the speaker again. Okay, so let's move to the last best paper. Last one is SQI sign compact post-quantum signatures from coordinates and isogenes by Luca De Feo, David Coelho, Anthony Mulu, Christian Petit, and Benjamin Veselovsky. So the talk will be given by Anthony.
By me, yes. Can you hear me?
Yes. Are you ready
Great.
for the presentation?
Yes, sure. Let me share my screen. Okay, it should be good, right?
Yes.
Okay, great. Perfect. So thank you for the introduction. So today I'm going to present to you this new signature scheme, SQI. So let's start with a quick review of the state of post-quantum cryptography at the third round of the NIST post-quantum competition. And here I put finalists and alternate candidates together. First, because otherwise there wouldn't be any isogeny schemes, but also because I think it gives a broader picture. And so isogenies are represented in this competition with one encryption scheme. which has the very nice properties of having very compact keys, but this comes with the downside of a quite poor efficiency compared to other solutions. So this competition was launched in 2016, which means that a lot of new protocols were introduced since then. And today we are going to focus on signatures. So I think a generic feature of isogeny-based signatures and protocol in general is that they have very compact keys. And this is going to be true for almost all protocols, unless there are some specific trade-offs that are made to reduce some other parameters. So modern days, there are basically 4 isogeny-based signature schemes which were recently introduced. And all of them are based on the same idea of repeating and transforming with the Fiat-Shamir transform to special sound identification protocol, which means that either these schemes will not be very efficient, or the signature size will be big, or actually both of them in the same time. And so in the recent work, I think there is only one that comes close to being quite practical, which is this CSI-Fish protocol, which is very nice, of course, but the problem with that scheme is that it actually needs sub-exponential precomputation. And this was only for, and to instantiate this scheme for NIST level 1 securities, I actually had to break some class group order computation record, which means that it's basically impossible to reach higher levels of security. And so from this table, I think it's kind of clear that we are still missing this ideal isogeny-based signature candidate. And of course, I'm here to convince you that SkiSign is this new ideal candidate. So this is a scheme that is derived with the Fiat-Shamir transform from a one-round high soundness interactive identification protocol. And before diving into the detail, let me just tell you a few of the nice properties that we have with this scheme. So first, this is the most compact post-quantum signature scheme if you look at public key and signature combined. So for instance, to reach NIST level 1, we have these sizes. Then we have, so we made an implementation of this scheme in C and Paris GP, and we obtained quite efficient verification and reasonably efficient signature. And before you're surprised by the times I'm going to give, just know that I put myself in the position of an isogeny-based cryptographer, and we are the kind of people who consider a scheme efficient if it runs in a few milliseconds and reasonably efficient in a few seconds. And so we actually obtain a protocol that can sign a message in 2 seconds and verify it in 40 milliseconds. So you see that there is a huge difference between signing time and verification time. This is partly inherent to the scheme, but also partly due to some choices that we made. Basically, there are some trade-offs to explore, but we choose to select the parameters that gave the fastest verification possible. And so the real downside of our new protocol is that we had to introduce a new security assumption to prove the security. And by new, I mean that it is an assumption that is really not standard and which is really ad hoc. So now let's take a quick time to introduce some of the notions in isogeny-based cryptography. So our starting point is actually elliptic curves over a finite field, which are the set of elements verifying this equation. And if we look at this set, then we have actually obtained an additive group. And in this additive group, we call scalar multiplication, which is the analog of exponentiation. Then an isogeny is a morphism between elliptic curves. And by morphism, I actually mean something that is going to preserve this group law through elliptic curves. And a very important feature of an isogeny is its degree, which in our case is always going to be the size of its kernel. So a quick example over the finite field in characteristic 11. So I take two curves, E and F here. Then I can define an isogeny with this very nice rational expression. And so this is actually a degree 2 map, which basically means that this isogeny is going to be 2 to 1 from E to F. And you can see it in some way as an analog of the squaring map. So now let's introduce endomorphism ring. So an endomorphism is actually an isogeny from a curve to itself. And the set of endomorphisms is actually a ring if you if you look at the addition and the composition. So a few examples of endomorphism. We actually saw one already, which is the scalar multiplication. And this gives a way to embed Z in any endomorphism ring of an elliptic curve. Then a slightly less trivial example, but still very important, the Frobenius map, which is a non-trivial endomorphism as soon as you look at an elliptic curve over an extension of FP. So endomorphism rings are actually really important with respect to elliptic curves, and we can actually classify elliptic curves with their endomorphism ring. So when the endomorphism ring is an order inside a quadratic imaginary field, we say that and so this is basically a two-dimensional object. We say the curve is ordinary. And when it is an order in a quaternion algebra, so a four-dimensional object, then we say the curve is supersingular. And today we're going to talk only about supersingular curves. And actually all modern day isogeny-based cryptography is based on supersingular curves. Unfortunately, I don't have time to introduce to all the nice protocols that we have for isogeny-based cryptography. But let me just introduce what is considered to be basically the underlying hard problem. And by underlying, I mean that if you know how to break this problem, you know basically how to break any isogeny-based protocol. And yeah, basically all the current isogeny-based protocol are obtained from variants of these problems, more or less. So this is so take two elliptic curves, E1 and E2. Then the problem is to find an isogeny phi from E1 to E2 of degree L to the E. So now let's talk about the Day-ring correspondence. So this is a very important mathematical tool for isogeny-based cryptography. And in the case of ski sign, it is really relevant because this is the study of this correspondence is what led us to discover the tools that we actually use to build ski sign. And then also it is very important to understand its security. So this correspondence is actually an equivalence of categories between the set of elliptic curve, supersingular elliptic curves under isogenies, and the set of maximal order in some quaternion algebra, depending only on P, under ideals. And so I'm sorry, I don't really have time to define what are orders and ideals, but in fact, this is really not important for this talk. Just remember that those objects exist and that we have a correspondence that basically gives us a dictionary to rewrite all the things that we could say on elliptic curves and isogenies on elements which lives inside a quaternion algebra. And rather than definitions, let me give you an example. I think it will help understand better. So let's take a prime P, which is equal to 3 mod 4. Then the quaternion algebra AP is actually the four-dimensional non-commutative vector space generated by the square root of -1 and the square root of -p. Then if I take this curve, E0, which is a very special curve, and we know when P is equal to 3 mod 4 that this curve is always supersingular. Then we have this very nice representation of the endomorphism ring of E0, given by these two endomorphisms, iota and pi, that we can actually make correspond to the square root of -1 and the square root of -p through our Day-ring correspondence. So in fact, pi is the Frobenius morphism that I already mentioned. And it is, and in fact, if you compose pi with itself, you obtain the scalar multiplication to by -p. And this is how you can see pi as the square root of -p. And then iota is this twisting endomorphism, which corresponds to the square root of -1. And you can see that we have actually very nice rational expressions for these endomorphism. So this is very nice, and unfortunately, this is a very rare occurrence of such a nice representation of an endomorphism ring. For almost all other supersingular elliptic curve, we don't have such nice formulas, which is partly why we are actually able to build cryptography on those type of objects. So now, one of the first thing I want to do with my correspondence is actually to look at my hard problem, my supersingular L isogeny problem. And actually, I can translate it with this new dictionary. And I'm sorry, there are a few notions that are not defined in this new quaternion L isogeny path problem, but you have to trust me that this is the right way of translating my supersingular L isogeny problem. And the nice thing, actually, is that this new problem is easy. In 2014, David Cohol and his co-authors introduced a heuristic polynomial time algorithm that I'm going to call KLPT to solve this quaternion path problem. And even though the proof is only heuristic, in practice, it actually works really well. And yeah, on basically all examples that we would need for isogeny-based cryptography. So this is actually an efficient and practical algorithm. But of course, this algorithm don't help us to solve the supersingular L isogeny problem. Otherwise, there wouldn't be any isogeny-based cryptography, as I said. So we still believe that this supersingular L isogeny problem is hard. Yet, this KLPT algorithm is a very powerful tool, as I'm going to explain. So I'll try to give a few problems that can arrive with the object that we have in this die-ring correspondence. And we're going to see that KLPT allows us to obtain very powerful results on those problems. So we start with our two basic problems. On the left, basically the supersingular isogeny problem, and on the right, the quaternion path problem. And as I said, KLPT allows us to solve this problem on the right, but we still believe that the left problem is hard. So then what kind of other problems we can encounter? Well, we have basically what we could call the effective die-ring correspondence, which is take a curve E and then find its endomorphism ring, okay? Or the counterpart, which is take a maximal order and then find the elliptic curve whose endomorphism ring is isomorphic to this maximal order. Then we can do the same thing with ideals and isogenies. And in fact, so in this paper of Kristen Eisentrager and her co-authors, which was published in Asiacrypt 2018, they were actually able to prove a few results on these problems. So in fact, they showed that all the problems on the right, which are all the problems that involves elements of the quaternion algebra as inputs, are actually easy. And you can use this KLPT algorithm to solve all these problems. And for the problems on the left, which are all the problems that arises from, if we start from elements in the elliptic curve world, then all those problems are believed to be hard, and actually, basically, they are all equivalent with one another. And in particular, this endomorphism ring problem is really the one that is considered to be fundamental in isogeny-based cryptography. Because as soon as you can solve this endomorphism ring problem, then we can apply this KLPT algorithm, which allows us to solve anything, basically. And this is really the take-home message of this presentation. As soon as you know the endomorphism ring, then you can apply this KLPT algorithm or variants of it, which allow you to do very powerful things. And this directly leads us to the proof of knowledge of endomorphism ring. Indeed, if I summarize what I just said, the knowledge of the endomorphism ring lets us perform very powerful operation. And this is the kind of principle that we really like in cryptography. So to the question, can we use this KLPT algorithm to prove that we know the endomorphism ring of some curve? The answer is yes. And so the first attempt was actually this GPS signature, so which was one of the signature I introduced in the table at the beginning of the presentation. And so this is a signature which is derived with the Fiat-Shamir transform from the repetition of a two spatial sound interactive identification protocol. Which is the reason why this scheme is not actually not efficient at all, and also that the signature size is not really compact. And this leads us to SkiSign, which can, in some sense, be seen as some kind of generalization and improvement of GPS. And so this improvement is obtained through basically new algorithms and new tools that we are going to introduce. Because otherwise, I think the idea of SkiSign is not really complicated. And what is really complex is this new algorithm that we introduced to make it possible. I think at the time of GPS, if they had the algorithms that we developed, they could probably have introduced SkiSign at that time. And in fact, our improvement can be divided into two categories. First, we introduced a new generic KLPT algorithm that allowed us to reach high soundness rather than repeating a two spatial sound protocol. And then also we were in need to bring new algorithmic tools to make this scheme practical, because this GPS signature was not implemented. And this is not because the authors were lazy or they didn't have time to do it. It is really because implementing this scheme and making it practical is a difficult task. And so a huge part of our paper is actually spent on developing the tools to make this scheme practical and make the implementation. So let me now introduce the overall idea of the scheme, because in itself it's quite easy. As I said, this is the complicated part is really about making it practical and instantiating this idea. So let me introduce the 2D lambda sound identification protocol. So we have a prover who wants to demonstrate the knowledge of the endomorphism ring of some public key EA. And in fact, the secret key can be seen as an isogeny from EA, from E0, a public special curve, to EA. So our identification protocol fits in the Sigma protocol framework, which means that in its interactive form, this is a 3-round protocol. First, we start with a commitment to a curve E1 that is going to be computed by the prover through a secret commitment isogeny psi. Then we have the verifier who computes a challenge, which is an isogeny phi going from E1 to a curve E2. And then the response from the prover is going to be an isogeny sigma from EA to E2. So the hard part of the signature is actually to compute this isogeny sigma. And once it is computed, then the verification is just, well, basically checking that sigma is indeed an isogeny going from EA to E2, which is a lot easier than actually computing the sigma from only the knowledge of the endomorphism ring of EA. So in terms of soundness, it's actually easy to see that basically the probability to cheat without the without the knowledge of the endomorphism ring is 1/degree of phi. Indeed, you can always start by generating sigma and then try to guess the challenge that is going to be sent to you, and you have basically probability 1/degree of phi to do that successfully. And in fact, we can show soundness with very standard and nice assumptions that are equivalent to this endomorphism ring problem that I introduced. So in terms of soundness, we are very happy about the security. And this was already the case for this GPS signature. Unfortunately, the problem is with zero knowledge. Indeed, we actually have to prove that this isogeny sigma doesn't reveal anything on the secret. And to do that, the best way of doing it is to prove that sigma is basically a random isogeny in some sense. But to do that, actually, of course, it depends on the algorithm that we are using to compute sigma. And the truth is that our algorithm does not give you a random isogeny. It gives you an isogeny of a very special form. But we actually believe that this special form don't help you to break the security. Yet we need a new assumption to prove that. And basically this new assumption is saying that the output of our algorithm is indistinguishable from a random isogeny. And I think from this brief formulation, you see why it is a very ad hoc assumption. So this is SkiSign in theory. You can see that we have a very nice diagram, which is not too complicated to explain. Now let's talk a bit about SkiSign in practice. So as I hinted, the hard part computationally is to compute the response isogeny sigma. And in fact, we have, as I said, we have basically to use this KLPT algorithm that works over quaternions. And so to get an isogeny in the end, we need to make a translation from an ideal to the corresponding isogeny. And this is really the hard part. And this is where we need new, we were in need of new algorithmic tools to solve that. So unfortunately, I don't have time to explain to you the mechanism behind this, this translation. Just know that if you want to look at kind of weird, but still nice isogeny diagrams, we have a few of them in the paper to explain this idea. So now let's talk a bit about the parameters. So to get the fastest verification possible, we choose to take the isogeny sigma to be of degree 2 to the f. Yeah, because for those who are not familiar with isogenies, basically the hardness of computing an isogeny is really depending on the factorization of its degree. And basically the smaller the dividing primes are, the faster the isogeny computation is going to be. So 2 to the f is really one of the faster kinds of isogeny that we can obtain. And then we have some requirements on the parameter to make our new algorithm efficient. And so in summary, we actually need a prime p. So, and I remind you that the prime p is the characteristic of the finite field that we consider. So we need a prime p such that p squared minus 1 is divided by 2 to the e times t. So where e is a small exponent that we want as big as possible. And t is a not smooth integer satisfying t squared roughly equal to p cubed. And this second constraint is one of the reasons why our scheme is not really efficient, because actually finding such a prime is hard. Indeed, any trivial way of constructing such a prime would rely on the fact that t is smaller than p. But here, t is bigger than p. So we can't do that. And basically, we don't have a lot of choice, but to basically search through a lot of primes. So there are ways to speed up the computation, but you can't avoid a big search. And we did this search and actually find a prime which is quite nice. So we find 256 bits prime p with e is equal to 33, f is 1000, and then t is this 2 to the 13 smooth integer, which I give the factorization. And of course, as I said, the smoothness bound is what is going to impact the performance. And in particular, you can see that the degree of, so t is divided by these 3,000, 4,000, 7,000. And these are the factors that are going to slow the computation. Because we are going to need, in fact, this parameter t is used because we are going to need to compute t isogenies. And so these are really these t isogenies are what is slowing up the signature. And in fact, you can estimate how much t isogeny we had to compute. And basically, this is a multiple of f divided by e, the exponents that we have. Okay, so this is for the parameters. And with these parameters, we obtain the implementation and the times that I showed you, which gives verification in 40 milliseconds and signature in 2 seconds, basically. So now let me conclude this talk with a few perspectives for the future. So we introduced the most compact post-quantum signature scheme, which is really nice. But now if I remove my hat of isogeny-based cryptographer, I realize that this scheme is actually really not efficient and still order of magnitudes below the competitors that we can obtain, for instance, from lattices and codes. And moreover, the underlying Sigma protocol has a very ad hoc security assumption, which is not very nice theoretically speaking, even though, of course, we believe that this assumption is hard. So here are a few directions for the future, which could improve various parts of SkiSign. First, there is definitely room for improvements in the implementation. For instance, we could find a better prime, which would definitely allow to speed up the implementation without making any practical theoretical change to the scheme. But there are also a lot of ways to upgrade the implementation. Basically, this translation from an ideal to an isogeny is a very complex mechanism, and there are a lot of isogeny computations everywhere, which definitely can be speed up, I think. Then we can look at some advances on this KLPT algorithm. In fact, this algorithm is basically used everywhere, and with several variants of it. And definitely improving this algorithm could allow us to gain efficiency or even gain security. For instance, maybe it could allow us to remove this new assumption with something more classical. So short of advances in that direction, we need to understand better this new zero knowledge assumption to start to have a bit of confidence in our security. And then finally, maybe the hardest and most important task, which is to find new algorithm to perform this effective direct correspondence. Indeed, basically, if we found a new algorithm for this direct correspondence, maybe we could break isogeny cryptography, or maybe short of that, we could try to obtain a better translation from ideal to isogenies, which could allow us to obtain a faster SkiSign. And so I'm going to stop there. Thank you for listening to me, and please ask any questions if you have some. Otherwise, you can look at the details in the full version of our paper. Thank you very much.
Thank you, Antonio. We have several questions on the chat. First of all, Devika, could you say questions?
Hi, can you hear me?
Yes.
Yes.
Hi. Thanks for the talk. It was quite clear and fun to listen to. My question is, if you go back to the slide where you described the SkiSign, once you know the endomorphism of your elliptic curve EA, yeah, this one. Once you know the endomorphism ring of EA, how do you compute sigma theoretically?
Okay, so the idea is to make use of this KLPT algorithm, basically. So if you remember what it does, it takes basically two endomorphism ring and then find an ideal between them of degree of norm L to the E. And this, through the direct correspondence, this corresponds to an isogeny of degree L to the E between EA and E2. So if you know EA, then you can also know E2 because you are the one computing psi and then computing phi, which means that you have an isogeny from E0 to E2. And this is one of the ways to obtain the endomorphism ring of E2. And so if you have the endomorphism ring of both curves, then you are able to apply this KLPT to obtain an ideal. And then you have to translate this ideal, as I said, into an isogeny to compute sigma.
Okay, thank you. And can you say what the new assumption is? Is the assumption that finding the endomorphism ring is hard?
No. So this is one of the classical and standard assumptions. So the new assumptions is really what I said about zero knowledge, which is that basically sigma, and because we compute it with this KLPT algorithm, which is basically finding a solution of some norm equation. And so the solution has a very special form. So in fact, sigma is not any isogeny. It's one very special isogeny. So to actually show zero knowledge, we basically have to assume that this very special isogeny still doesn't reveal anything on the endomorphism ring of EA, which is our assumption.
Okay, thank you.
Yeah. Okay, thank you. So next question is from Stephen Galbraith.
Yeah, so I can see the question is, okay, you can ask them yourself. Very good.
I was going to say, thanks, Antonin, for your talk. It was very nice. Yeah, I've got a couple of questions there about really rebalancing the parameters.
Yeah. So yeah, I see you. First, you want to know if we can choose parameter to balance sign and verification time. So actually, there are some ways to do that. So we did not explore them in the implementation. But basically, the idea is that we choose to take the degree of sigma to be 2 to the f for very fast verification. But this basically slows up the translation. But what we could do is choose, for instance, this is one way, okay, of speeding up signature, would be to choose the degree of sigma to be 2 to the f prime times t, okay? So now for the verification, you have to compute an isogeny of degree t, which is a lot slower. But for reasons that are not clear if you don't know how the translation from ideal to isogeny works, this would allow to speed up significantly the signature time. I don't know if that was, this is satisfying your question.
Yes, that's good, thanks. The other question was really about the sieving, if there's other ways to find good primes.
So yeah, so I'm not really the expert on that part. In particular, I wouldn't have any idea about quantum algorithms. Yeah, so I'm not sure. In any case, since you are looking for smooth primes, I guess that factoring is not a problem for these algorithms. Oh yeah, I don't really know, sorry.
Okay, so final question is from Wang Winning.
Yeah, so I think these kinds of is overlapping with Steven's question. So as I said, yes, there are some trade-offs to explore. I gave one of them. There may be others. But the idea is, yeah, you could have faster signing time by basically changing the degree of the isogeny sigma that you can compute. We have actually full liberty to choose the type of degree we want. It has to be of a certain size. Okay, so it can't be as small as we want, but as soon as the requirement is okay with it being a given fixed size, basically, we can fit any kind of factors. We can fit power of 3s, power of 5s, whatever you want. This is just really a choice.
Okay, thank you very much. So, now, we have. Okay, we have prepared this paper award certificate, and we will send you later. And congratulations again. And everyone, please give all the award winners a big round of applause. Thank you very much. So we'd like to close this session.